Hello everybody, my name is Viktor Galitsky and I gave the first 8 lectures in this course exploring quantum physics. Today it is my pleasure to welcome those of you who survived this course to the last concluding lecture of exploring quantum physics. So this lecture is going to be on the very interesting subject of time-dependent quantum mechanics, and we're going to talk about it a little later, but first I would like to take a couple of minutes to talk about the final exam coming up. So the format for the final exam is going to be slightly different than that of regular homeworks. So there are going to be 16 problems, roughly one problem per every lecture, and these problems intend to cover all the material that we have studied in this course, including this lecture and starting from the very first lecture. So the final exam will be due 2 weeks from now being the time when we posted these last lectures. The deadline for the final is going to be the same as the hard deadline for the last posted homework. So you will notice that there is no homework for this last week, no regular homework, but there is a final exam. Also, you will have just one attempt to take the final, unlike the homeworks where you have multiple attempts. And once you start, there will be a time limit of 6 hours for you to complete the final. But you shouldn't worry too much about it, because the final exam should be a little bit on the easier side as compared to the last homeworks you've seen in this course. So if you've got this far, you certainly should take the final and get your certificate, or probably a certificate with distinction. I'm sure many of you will get those. So in other words, if you have so far completed most homeworks or all the homeworks, you definitely should take the final. Don't even think about it. It's going to be pretty straightforward and you will do well. Now, going to the scientific part, well, to the lecture. So I've been sort of thinking a lot about a possible subject for the last lecture. And of course, there are many possibilities because there's a lot of material we haven't had the time to study, unfortunately, due to the time constraints and some constraints on the format of these lectures. But I decided to talk about this subject, time-dependent quantum mechanics, for 2 reasons. So the first reason is that this topic of time-dependent quantum mechanics is among a very few topics in theoretical physics that is still being developed. So it's still a very active subject, research topic in theoretical physics. So this is different, by the way, from most other things we have seen in this course, where pretty much everything we want to know, we do know. So of course, people are still arguing about foundations of quantum physics, some philosophical interpretations of quantum theory, etc. So these discussions will probably continue forever. But once you accept the axioms of quantum mechanics and look at it from the practical point of view, so we can pretty much explain or predict the result of any conceivable experiment that can be performed with quantum systems. So the problem, I would say, not with mysteries of quantum physics, but with lack of mysteries at this stage. We actually understand pretty well what we see. But this subject of time-dependent quantum mechanics is a bit different in that there are still some open questions. I wouldn't call necessarily these questions grand mysteries, but they're definitely open problems and frontiers which we're still exploring. So this is one reason. So the second reason I have chosen this subject is because I myself have been working on it quite extensively for the last few years, and this is among my sort of chief research interests. So of course, what I just told you sort of implies that, well, I hardly can tell you all these interesting things about time-dependent quantum mechanics in one lecture. So it's a very active research topic. It could be a subject of a separate course. But at least I can sort of give you a flavor of what time-dependent quantum mechanics is about. And also maybe one message of this lecture would be for you to understand why this subject is difficult. Why, unlike in most other subfields of quantum physics, here we're still sort of struggling to understand at the technical level what's going on. So this would be another sort of message of this lecture. So what we're actually going to be studying in today's lecture is truly time-dependent Schrdinger equation. So we actually derived, well, in quotes, this equation in the very first lecture of the course but we never truly used the time-dependent part. So in some sense, we got rid of it the first moment we got the opportunity to do so, because in most cases we have looked at, so the potential, well, actually in all cases we have looked at, the potential was not time-dependent, the potential was constant. So what we're going to be studying today is the situation where the Hamiltonian h is a function, explicit function of time. So it's not a constant, it's a function of time. So of course, even if it were not to be a function of time, even if the Hamiltonian were a constant, so the wave function would still have been time dependent, and the wave function would be we had talked a little bit about this when we were deriving the Feynman path integral. So the wave function as a function of time in this case would have been the evolution operator e to the power minus I over h bar h t acting on an initial condition that we assume is known. Now if the Hamiltonian is a function of time, so this of course doesn't work. So this in this case doesn't work, and basically we don't know a priori what the wave function is now, but this is exactly what we want to know. So basically to solve the time-dependent Schrödinger equation means either to find the wave function psi of t explicitly, or even better, to find the evolution operator u of t that would relate the initial condition to the final wave function. So again, in the case of time-independent Hamiltonian, so this evolution operator is written here. So this is this exponential e to the power minus I over h bar h t. So but if the Hamiltonian is explicitly a function of time, well, there is no simple closed equation for this. One thing I should reiterate about this evolution operator, which is true both in the case of time-independent Hamiltonian and in the case of time dependence, is that actually evolution operator is independent of the initial condition. So it essentially describes a rotation of the wave function in the Hilbert space. So let us recall that, well, wave function describes, well, has probabilistic interpretation. Okay, and so if we take, let's say for discrete spectrum, if we have, let's say one particle in the system, so the wave function must be normalized to 1. So, and it's true both for the initial condition and for the time-dependent part. And it should remain 1 just because if we have a single particle in non-relativistic quantum mechanics, it's just going to stay there. It's not going to be it's not going to disappear, and new particles are not going to appear out of the blue. Well, actually in quantum electrodynamics it is possible, but we're doing non-relativistic single particle quantum mechanics. So this normalization condition should be preserved. And so if you think about Hilbert space, again, as a vector space, let me just erase this error here. So if you think about the Hilbert space as a vector space in which our wave functions leave, so what this condition implies in some sense is that the wave function exists on a hypersphere. Well, I cannot draw it in higher than 3 dimensions, but of course we should sort of take this picture with a grain of salt. So it's some multi-dimensional Hilbert space, and there is some sphere. Well, it didn't work out very well. Let me just redraw it a little better. So if we have a sphere, well, it's not much better, but anyways, you understand what I'm saying. So this sphere is essentially a manifestation of this condition. It basically means that my wave function exists, you know, the normalization condition is preserved. So this essentially means psi squared is equal to 1. And if I start from some initial condition on this sphere, so let's say this is my psi naught, and the only thing which can happen with this psi naught is that it can sort of rotate in this Hilbert space to a new psi of t somewhere else on this sphere. And the operator u essentially enforces this rotation from psi naught to psi of t. So we already discussed it, as a matter of fact, during the derivation of the Feynman path integral, but it was in the middle of, you know, this optional technical derivation, and I'm not sure if all of you have looked at it, but I think it's a very important message that actually u of t rotates the initial condition essentially by some angle in this multidimensional Hilbert space to a new time-dependent wave function somewhere on this hypersphere which exists due to this normalization. And the important thing is that if we were to choose, let's say, a different initial condition somewhere, well, let's say here on the sphere, so the and if we were to apply the same time-dependent Hamiltonian or time-independent Hamiltonian, so in both cases, so the rotation would be sort of by the same angle. So it would be different, let's say, psi naught prime and psi prime of t, okay? But the evolution operator, this guy, would be exactly the same, okay? And so this is, that's why I say even better, you know. So of course we want to find, in a particular case when we're dealing with a wave function, so we want to find the wave function as a function of time because it will essentially describe everything we want to know about the system, all the probabilities, all the transitions between various states and amplitudes. But if we know the evolution operator, we in some sense can solve all possible initial conditions in one shot, just because the evolution operator is going to enforce this quantum evolution just by acting on an initial condition. But, well, the problem with it, as I mentioned, is that it's very hard to find the evolution operator. Now, why is that? Why is it so difficult? So let me sort of give you a very brief explanation why it's difficult. So if you look at this expression, this equation, and if for a second, so let me just write it here in quotes, in some sense, this initial condition, if for a second we assume that the Hamiltonian is not really an operator, but some, you know, just some function h of t without the hat. So then I can simply divide this equation, let me put it in quotes because this is not true. So if we divide by psi of t and integrate both sides of this equation over time, we can write the solution to this sort of Schrdinger equation, dumbed down version of the Schrdinger equation, as e to the power minus I over h bar, an integral from 0 to t, h of, well, some t prime, let's say dt prime, and here is going to be the initial condition psi naught. So this would be a solution to an ordinary differential equation, time-dependent differential equation of the first order. So if you look at it, that's what it is. So it seems very simple. So why don't we just write that and put a hat here? So it turns out that we cannot do that. And, well, those of you who are interested should take the time and, well, stare at this expression for a little while and, well, work with it a little bit to see why it is the case. Well, why it is not the case, actually. Why this is not true, that in the case of a true operator Schrdinger equation, so this solution doesn't work. And the chief reason for that is because the Hamiltonian h of t does not commute with itself necessarily at different moments of time. So if we take two different moments of time, let's say h of t1 and h of t2, so the Hamiltonian is not going to be, the commutator of the Hamiltonian with itself at different moments of time is not zero. And this is a major complication which makes all quantum mechanical, time-dependent quantum mechanical problems extremely difficult. And this even involves even the simplest versions of this problem, let's say with the spin 1/2 with two-level systems. Even there is no, generally no closed solution to a time-dependent problem. So let me just leave it here. So now let me provide a couple of general examples of time-dependent quantum problems. So the first example will be the following. So let's imagine we have a particle which is moving in a potential v of r. So let me just draw a v of x here. For the purpose of illustration, let me just assume it's one-dimensional. And let's imagine that this potential itself is sort of breathing. So it's moving as a function of time, for example, or it's changing as a function of time. And as time goes by, let's say it may become different. And so the question that one may ask is what happens with the particle, with the quantum particle, moving in this potential. So how does this wave function change as a function of time? So even if the potential were constant, so we know that it's, strictly speaking, a rather non-trivial problem to figure out the energy levels in this quantum potential. And at any moment of time, we can define sort of an equivalent time-independent problem and find the corresponding energy levels. But if the Hamiltonian is time dependent, the energy itself is not conserved. So this would be a wrong question to ask in some sense. What are the energy levels in the problem? So we know that at any moment of time there is formally a time independent sort of eigenvalue problem, but unless the potential is changing in time very slowly, these energy levels do not have a meaning, because we're always sort of pumping in energy in the system and the energy is not conserved. So this is really one of the major complications. But the probabilistic interpretation of the wave function is still valid, and we can still ask the questions about, well, the probability, let's say, of finding a particle in a certain region in space. So, and it's still going to be given. So this probability is still going to be given by, so let me just write it here. It's an example of probability, let's say, to find a particle between points x1 and x2 is going to be given, well, it's a function of time. So let me write the time here. Is going to be equal to the integral from x1 to x2 psi of x of t, everything squared, integrated over dx. So this is an example of a physical observable property that we can calculate using a solution to the Schrdinger equation if this solution is known. Now, the second kind of problem, well, it's actually the same time-dependent Schrdinger equation, but for a different type of a system, is, let's say, spin in a time-dependent magnetic field. So this relates to the lectures of Professor Applebaum, who introduced spin, and in particular, he was talking about nuclear magnetic resonance, MRI imaging, for example. So where actually what's being done is that the spin is being rotated by a time-dependent field. So, and in this case, the Hamiltonian, well, the wave function, first of all, is a two-component spinor, and the Hamiltonian here, so this is our h of t. So in this case, the Hamiltonian is simply b dot sigma, sigma being the vector of Pauli matrices, and this Hamiltonian 2x2 matrix acts on this two-component spin. And essentially, this is a first-order differential equation, and the problem here would be, let's say, to find the this psi of t again. And in this case, for example, the absolute value squared of this psi up of t squared, this would give us the probability of finding the spin in the state up at the moment of time t. So this would be another observable characteristic we can talk about. Now, an amazing thing actually, and I have to admit I didn't know it until just a few years ago, is that this equation is actually, well, it's 2x2 matrix, time-dependent first-order differential equation for a 2x2 matrix. So this equation appears not to be solvable in elementary functions. You cannot solve this equation in general, analytically at least. And so when I first looked at this equation, I thought, well, I will just solve it during my lunch break. I didn't even want to look into the textbooks. I just thought it was just a toy model of some sort. But it turns out that even this equation, maybe the simplest quantum mechanical problem we can think of, 2x2 matrix or two-component, two-dimensional complex Hilbert space, even this problem is not exactly solvable for a general h of t. So this gives you something, well, some sort of insight into the complexity of the subject. But as usual in theoretical physics, if we can't solve the problem exactly, it doesn't stop us from solving it by some approximation methods. Actually, I should mention that one major omission in this course was perturbation theory, which is a general theory of solving approximately various stationary quantum problems. We didn't talk about it, but it's a very, very important piece of quantum mechanics that those of you who are interested in professionally pursuing physics you should definitely look into this subject. But in this context, in the context of non-equilibrium or time-dependent quantum mechanics, there exist similar methods, various approximation schemes, and there are two clear situations, two clear sort of asymptotically opposite cases of either very fast perturbations or very slow perturbations, or so-called adiabatic perturbations. So let me just write it down. And so we're going to study actually in the next lecture. We're going to study fast or sudden perturbations, which means fast changes in the potential. And in the third part of this lecture, we're going to discuss slow or adiabatic perturbations, which lead to very interesting so-called topological quantum phase that appears in the solution to the Schrödinger equation. So just sort of to wrap up this first introductory part, let me first define what we actually mean by fast and slow. So as we discussed throughout the course, actually, well, if you are talking about a physically a quantity which has a non-trivial physical dimension, be it the length or time or whatever, so you can't really say that it's small or large unless you compare it with a quantity which has the same physical dimension. So when we have a time scale, let me call it, for instance, tau of a certain time-dependent perturbation. Let's say this is a typical time at which a potential changes. So in order for us to see, to define whether it's short time scale or long time scale, we have to get another quantity to compare with, which has the same physical dimension. And it turns out that in the case of quantum problems, if we have a spectrum, so let's say this is our energy, okay, so let's say these are different energies, and there are some level spacing between the neighboring, let's say, energy levels. Let's say in the harmonic oscillator case, it would be h omega. In the case of potential well, it will be something else, and they will in general change with time. So, but let's say if we have a system which is a quantum particle, which is, let's say, sitting on a certain quantum level or neighboring levels, so the appropriate energy scale associated with it is this delta, this level spacing. And h over delta is another time scale. So this is a time scale to compare with when we're talking about fast or slow perturbations. So if tau is much smaller than h over delta, we will say that this is a fast or sudden perturbation. If, on the other hand, tau is much longer than h over level spacing, we're going to be talking about slow or adiabatic perturbations. And these are going to be the fast and slow perturbations, again, are going to be the subjects of the next two parts of this lecture. Now, just the final thing I'm going to say here is that those of you who are interested in research on these sort of quantum dynamical systems and in sort of exact non-perturbative methods of solving quantum problems. So I gave a lecture, well, it's a research level presentation, but I think it should be understandable to most of you. So I gave a lecture on this subject at the Kavli Institute for Theoretical Physics a couple of years ago, and so if you are interested, you may want to take a look at it. Of course, there are a lot of other people working on this, and they have a number of amazing results, but I think there is there is an interesting development in this field which allows us to construct exact solutions. But unfortunately, it's well beyond sort of the scope of this course and the level of this course, so I just put a link here. So if you're interested, take a look. Otherwise, we'll talk now about the sudden and slow perturbations and see how quantum problems can be solved in these cases and what new phenomena appear there.